Okay, good morning, everybody. I'm Frank Jalinoos. I work for Federal Highway Administration. I'm running a lab at Turner Fairbank. It's a corrosion lab, and I previously run the NDT lab. My background is basically geophysical engineering. So, all right. So the basically outline. I'm going to talk about the whole reuse issues involved with our foundation reuse, mostly in the bridge environment. I'm going to then take a look at two aspects of it. One is durability testing, which is mostly corrosion testing that is done. One is structural integrity testing with some case studies. Again, my slides are not moving. So somebody else, maybe Carol, you move the next slide.
Please click on the slide to accept control.
Okay.
Well, maybe it's better if we just if it still
Okay,
doesn't move. Okay.
Did you move? Okay. So I guess you're going to change the slides from the. Oh, okay. Now I can move. Okay, good. So foundation reuse basically involves in reusing part of or whole of the foundation as is, but often it involves evaluating the bridge for new loads. Now, on bridge environment, foundation reuse often involves the reuse of the whole substructure, the columns, because they want to keep the same span length. So that's often is the reuse of substructure involved. And in bridge environment, that's often when a replacement, a bridge replacement project or widening project or repurposing is the three main causes of this. Well, what is motivation was well mentioned in the two previous presentations. The main one is economical because they get major saving in reconstruction and demolition costs. Now, in bridge environment, you got the right-of-way issues. Whenever you have a new alignment, especially in the urban corridors, that's very costly. Utility coordination and user cost is substantial because foundation reuse is accelerated construction, so you have savings in time, and the impact on community is extensive. Bernie also talked about the environmental aspects. You don't have to go through the very extensive environmental permitting that's needed for the new foundation, the waste management, and of course, carbon emission issues that was discussed by Bernie is also implies quite a bit here in bridge environment. On the social aspects, there's a time savings, so it's a impact on mobility and traffic management, of course, work zone safety, and cultural preservation is also a big issue. So it's a big sustainability that's involved in foundation reuse. Okay, so now what are the options? I'm showing two options which does not involve reuse. This is generally what's happened in the bridge environment. Option one is you build a new alignment next to the existing one, as it's done here. This is a new alignment with this steel girder bridge. So once you're done with this new alignment, you change the traffic from the old bridge to the new one, and then you start demolishing the old. Okay, so that's a kind of a parallel structure on a new alignment is option one. When you build it in place, when you demolish the old bridge, that we call option two. Sometimes you keep parts of an old foundation, as was the abutment here, that's used for scour, but then you build a new foundation on the back of it. So these are not reuse. This is what's done as state of practice. Now, reuse is two options. Option three is you reuse the whole foundation as is. Basically, you don't add any capacity to it. You do some repairs on it. And option four is that you enhance or strengthen the foundation. The number of options might be putting in new drill shafts or micropiles or doing ground improvement, or maybe even widening the pier cap. So these are just a composite figure showing multiple options. On as is, the example, a very prominent example is our bridges in I-95, and they were involved with 11 bridges which had to replace. So what they did is they first used they reused the foundation as is, but they did some corrosion testing and corrosion repair, which I'm going to go over it later in my presentation. And then on successive on weekends, they brought in prefabricated bridge elements and they demolish and place it in new section by section. Okay, so they only maybe close the traffic 3-4 hours. You know, that's I-95, and they did it just on the weekends, and it was involved with 11 bridges, and the total saving was $60 million of reusing foundations. $60 million, quite substantive. Here, down the bottom, they enhanced the foundation by basically putting a new rebar cage. They around the existing pneumatic caisson, and they sort of widened the 4 piers on the river. And again here, they prefabricated the steel truss. They brought it by barges. They created these temporary piers. They put it on the piers and they slide it 50 feet into place. Okay, so they demolished the old bridge. They brought these sections of truss bridge, they put it on this temporary bridge and put it in place all in 3 days. So the impact was only 3 days replacement. We call that accelerated bridge construction using prefabricated elements. But the reuse, the net effect of reuse was $50 million in saving. So it was, again, quite substantive. But all the testing is done. It's very small incremental of the savings that is done. So these this is called slide in place type of construction. Okay. Now the idea of the reuse for bridges are fairly new, but as Bernie mentioned, that it's been around for buildings quite a bit, and there was a European effort called Reuse of Foundation for Urban Sites, or RUFUS project, which culminated in this best practice guideline, which was published in 2006. It was between 2003 and 2006. Basically, 5 European countries. It was France, Germany, UK, Sweden, and Greece that were involved in this. And so the work is done, and the best practice is published. It basically talked about reuse of small diameter piles that's done in the urban corridor, especially like in Chicago. And they even created a test site in BAM, which is in Germany, which is counterpart to Turner Fairbank. They created small diameter piles with pre-engineering defects, and they did a lot of NDTs with pulsosonic and sonic echo and parallel seismic and all that sort of stuff. So they took a look at it back in 2006. But now in 2014, on the bridge environment, we ran a workshop on foundation reuse, which created this tech brief back in 2014. 3 years later, NCHRP, National Cooperative Highway Research Program, created a synthesis of practice, what the states are doing in foundation reuse. They created this this synthesis report back in 2017. Andy Bachman wrote this, and it sort of documented what the state practice is in this area. So that's 2017. So 2014 was our workshop, and then we started a research program, which we published this report in 2018, which basically look at this whole foundation reuse in all aspects of its different chapters, starting with risk models, doing a death study, structural integrity assessment, durability and load testing, use of innovative materials, and design of new foundations for reuse. Well, today I'm just going to talk about the integrity and durability aspects of this. If you want to take a look at this document, you just do a web search, a Google search, just say FHWA Foundation Reuses, and it should be the first or second entry. You can get this report. So, okay, so what you do, the first thing you want to do in the bridge environment is do a sort of a death study. You go over all the records about the foundation and you look at the foundation performance. You look at the design, installation, soil exploration, similar to what John did in Boston. Now in the bridge environment, we also have inspection records every 2 years. Every bridge is required by us to be inspected. So those are called routine inspection, or you can have damage or special inspections if there are some special issues on the bridge, and if there are scour issues, to do underwater inspection. You want to go all the records just to see. That's the first step you want to do, including a bridge visit. Then the next thing you want to do is the corrosion study. So you start again with looking at the corrosion records on the elements that you're taking a look at. For example, you want to look at the piers as it was in I-95 projects. Then you go in the field and do some NDT inspection. That's the second step. And then the third thing you do is modeling for what is the remaining service life of the bridge member you're trying to reuse. So again, the process is you go out in the field, you first do a visual test. Say in the column, if you have a concrete column, you look at the visual cracks, or do a delamination or sounding or impact echo testing. Then you look at the corrosion or corrosivity of the element by doing half cell potential or GPR or even resistivity test. And then once you figure those areas, then you want to core into it and get the chloride profile, and then you want to do repair and get the chloride out so that it makes that component suitable for reuse. Okay, so this is the steps that are taken on corrosion testing. Let's take a little bit of time. So here's a test for ground penetrating radar. You go in the column. Bernie mentioned also, so that you basically, this is a line of data. These hyperbolic events are reflections from the steel. Okay, so the tip is where the rebar is. So the time of flight it takes to go back and forth. It gives you the cover depth, which is very important, because if you have areas of low cover, that's probably where the corrosion is happening. Whenever you have chlorides or moisture or corrosion products like rust into the concrete, that makes it conductive, and that attenuates, damps the signal. So, and then that's the area that's probably corrosion is happening. So that's shown here. Or you can just simplify it and just take the amplitude of these areas and create these heat maps, and lower amplitude areas like this red areas is where the corrosion is happening. Another test that's often done is called half cell potential. I guess I have a little delay. Okay, it's coming up. The half cell potential testing. So you basically core into the concrete, into the rebar. You connected that. It's kind of like a voltmeter, and you measure the difference in potential from the surface to the rebar, and then you map it out here. So whatever you have low values, that indicates areas of high probability of corrosion. So that's a ASTM standard, very simple but effective test that's done here. So once you figure out where the corrosion areas are, you typically core and you do a chloride profile, do lab testing at this point. You take a look at where the chloride profile is, and you do other tests like petrography, you look for ASR issues and so forth. So, and then once the core result, the lab results and field results they're done, then you do modeling for the remaining service life. Then, so once you figure out what the remaining service life is, so what is the, how are we going to repair the bridge element? The most common one is a cathodic protection, where you inject a direct current to the metal, to the corroded metal, which is the rebar, and essentially turning it from the anode, which is where the rust occurs, to making it a cathode. Okay, so you're sending a current. So at that point, the corrosion process really stops. And so there's two ways of doing that, but one is by impressed current, or the other one is galvanic. You put a sacrificial element on the pier itself, so that would preferentially corrode. So this is very important protection, especially in a marine environment, aggressive environments. So that at this point, especially like say down there in Boston, that might be a option for doing this to stop the corrosion to occur any further. Another method is to clean the concrete from any chloride that's in there. It's called electrochemical chloride extraction, where you inject the current to the rebar, and then you're pushing the chloride out. You put a temporary anode, basically a conductive mesh, to get the chloride, which is it's going to driven back out. So reverse the process back into this conductive medium. It takes about a month or two. This is a process that was done on I-95. Of course, the traffic was not stopped, so the columns, they basically were cleared of the chloride, and they did some patching. And then once that was done, then they replaced the superstructure. So this is similar to cathodic protection, except cathodic protection, you don't have a temporary anode, you have a permanent anode, and you put less current, about 10 milliamps per square meters. This is about 1 amps per square meters. You basically keep the steel not to corrode. That's the threshold that corrosion doesn't happen. But you have to make this as a permanent connection. You have to have rectifiers to make sure that this current is constant, because there's temperature dependency and moisture dependency. So it's an involved process, cathodic protection, but it's well worth taking a look at, especially in marine environments and splash zones and so forth. So I'm now going to shift gear and talk about structural integrity assessments, and that typically involve a lot of NDT. I already talked about GPR and impact echo and UPV, and Bernie talked about sonic echo and impulse response and parallel seismic and use of gradiometries in boreholes. I'm going to talk about different aspects of structural integrity using geophysical logging. To do that, we're going to have a bridge that we had in as part of our central federal land. It's close to Flagstaff, Arizona, about 40 miles south of Flagstaff. It's a federal land bridge. It has very low traffic, about 2,000 cars per day. So it's a perfect site for doing a lot of testing. It's a 3-span, 2-lane bridge. It was 104 feet long, and it was 25 feet. And the central span was 50 feet, and the other span is 25 feet. It was basically built in 1934, and it was widened in 1968, and it was widened again when we were doing the testing, and there was hence that was the reason for it. So there's two aspects of the foundation: old foundation 1934. I'm going to show some results, and the newer foundation, which was widened, and they use a concrete pad on top of the bedrock. I'm going to show some example. So that was the bridge. It was a stone masonry wall bridge. Okay, so what we did, we cored from the deck all the way through the steel girders, all the way through the bedrock, through the foundations. We put a pair of cores for each of these foundation walls. Okay, and what was the coring cost? It was about $150 per linear foot. So a 50-foot coring costs us about $7,500. So a pair costs us about $15,000. So there's a way of doing that, and there's a lot of lessons learned, but very effective. And you get, of course, the cores coming back. So again, I'm going to use it what's known as borehole logging, or what we call core hole logging technology. I'm going to use basically optical televiewers and acoustic televiewing. I'm going to show some examples for mapping cracks from the core holes, and looking at elastic properties using sonic and density tools, which is similar in the drill shaft environment that Bernie showed with the cross-hole sonic and 4-pi density. These are other logging, which I don't have time to show examples right now, but we look at extensively this whole idea of borehole logging. So the next slide, I'm going to show, this is shown, the first one is the optical televiewer. So we have the optical camera that you're putting in down the borehole. And the tool has a 3-component magnetometer. So similar to the magnetometer that Bernie used to correct for the changes in azimuth as the tool rotates as it goes down the core hole. And it also has 3-component accelerometer to correct for inclination. So what you have is an oriented core. So you can look at it in 360 degrees. Just open it up like this, so you can see the whole borehole contact information in full oriented, and then you can get the strikes and dips of any feature that you want to take a look at. So that was the concrete pad on the new foundation, and that was the bedrock, and see the contact was pretty good. Okay, you can also use a acoustic televiewer. Here you have to have the core hole filled with water and use ultrasonic waves in kind of a sonar, and then you can get reflection back from the walls, so you can look at it ultrasonically this way. Now, if you see any bugs or issues in here, you can find what the depth of it is, kind of like a sonar, and this is shown here. You can also use a caliper arm, that is a mechanical arm that shows what the depth of these bugs or these components are, as shown in here. Okay, so that's acoustic televiewer, this one here, and optical televiewer. Now on the old foundation, we found these very much openings here, which was unexpected, and they were subsequently grouted by our Central Federal Land Office. So you can see it, but this is optical televiewer. This is the caliper, the mechanical caliper. You can see how deep they go. And of course, in the bedrock, you can look at the strikes and dips, and these are Rhodes diagrams. So it's a very effective technology to use for foundations. It gives you a complete view of what's going on down the core hole. The second one is what we call physical properties. So it's similar to that cross-hole sonic that Bernie talked about. Here we have a sonic tool. Basically, we have a sonic source, which is a single impulsive source, not a resonant pulse source, and number of receivers in line down the borehole. So we're looking at the time difference as the wave travels up the core holes, so they get the velocities in place. So we get a full waveform, just similar to that cross-hole sonic, but this is, it's not as a resonant signal, so we can pick the compressional wave and shear wave. So we can pick the velocities, compressional wave velocity and shear wave velocities. Also, we have a different tool we call a compensated density that it gives you a calibrated density measurement. Now, if you have velocity and density measurements, then you have all the elastic moduli information. And so doing, you can get the Poisson ratio as the black curve shown here, as well as Young's modulus, shear modulus, and bulk modulus. So you can get all the modulus information continuously every inch from the top of the core holes down to the bedrock. Here was the moduli information, the concrete pad. This is in the stone masonry. This is the bedrock. So this is a physical property measurement, quite effective. Okay. Of course, if you have a pair of core holes, you can do a cross core hole measurements. But here you need to have this, just like that cross-hole sonic logging that Bernie showed. But here we're using the geophysical, because of the distance involved, we use hydrophones and seismic sources, and then use many different angles rather than just looking straight across. We have, for every source, have many different angles, and you can do this tomographic imaging of the whole of the foundation, including the bedrock. And these were with the issues were with the those holes that subsequently our Federal Land Office routed in. The other option is using surface geophysical methods. If you want to look at the condition of the soil and bedrock, here we ran seismic tests just parallel along those walls, those four foundation walls. This abutment, pier 1, pier 2, and another abutment walls, and two cross ones. So we create this fence diagram. So you can see here that the bedrock in red, and you can see there's no issues in it, and there was hardly any dip. So of course, this was a research program. So we had a lot of research money. So we want to look at the capabilities of different methods. So we threw everything at it. We run 3D resistivity, did a lot of NDT, and that's what's all in the report. This advantage of working in a research environment, because you're basically trying to push the envelope and trying up a new methodology. You're basically looking at capability rather than a specific need. And in that case, you have to work within the budgets within the projects, so they can't do too many new ideas. There were a lot of publications in this. This was about 5 years ago that I finished this project. When I'm looking again on the corrosion side, if you want to look at these publications, you just do a internet study of FHWA FCP. FCP was the name of the project, Foundation Characterization Projects, and then you can get access to some of these reports. These are the two federal highway reports. There was a magazine article in Public Roads, which are our magazine. We put an article in Geostrata and Aspire, which is a structural article, and a number of journal articles, about 5 on all aspects, quite a bit on load rating of superstructure, substructure, combined load rating, and all that. If that fancies your interest, this is all listed in this page. You can access those. So it's our standard disclaimer. We don't excite or promote any industry partners. And so that's all I have.